Welcome you back to the next to the course on inorganic chemistry of life. In the previous class we have looked at aspects related to spectral methods such as method on mass spectrometry, method on fluorescence spectroscopy, and we have been looking at the NMR spectroscopy. I said I will show some examples to study both the dynamics of this as well as the paramagnetic relaxation things too. Yes. So, what we looked at in the previous case was that the spectrum, when you have a diamagnetic, that means no paramagnetic species, that will come the proton NMR spectrum will come in 0 to 10, 0 to 15 ppm. Once you have a paramagnetic center in that, they will shift to any extent depending upon the contact shift. So, these are referred as the contact shifts. One example shown on the left side is that a cobalt 3 plus, which is a D6 system, and this D6 system having all electrons being paired becomes diamagnetic, and it comes as if like if you take just a phenanthalene moiety NMR, or you take its cobalt 3 complex, it will be alike. On the other hand, instead of the cobalt 3 plus, you take just cobalt 2 plus. All that you have is just one electron difference. So, one electron, now it is a D7 system, and the D7 system resulting in a paramagnetic center, the cobalt center, cobalt 2 plus center. So, the coordination is the same kind of thing, but that will shift the proton resonances to even 100 ppm. So, going from very small region of this within 10 ppm to about 100, 110 ppm, as you can see all of these. This kind of thing is a boon in disguise, because the paramagnetic contact will shift these ones to a greater extent. Okay, on the right side same thing as shown example of the hexanol, and hexanol has got all these CH2 groups, the 5 CH2 groups, 1 CH3 and 1 OH. The OH is seen, the CH3 is seen, but all the CH2s have come within the small region. But now if you add some paramagnetic reagent like some kind of an europium species, that europium species will bind to this and to different extents at the, of course, at the alcohol position, and that will bring a contact shift on the methylene, first methylene, second methylene, third methylene, etc. The maximum will be in the first methylene, less will be in the second methylene, third methylene, etc., etc. You can see, and this kind of a contact shift will resolve all the CH2 groups that are buried under this particular envelope to this kind of thing. So, is it not a great boon to have a paramagnetism? While the organic chemists think the paramagnetic, they call it as an impurity, and for inorganic chemists, bioinorganic chemists, biological inorganic chemists, that impurity, what they think, is actually a boon in this. So, in metalloproteins and metalloenzymes, you have a lot of transition metal ion centers. Many of those transition metal ions could be paramagnetic, and then when they bind to the protein, one can study their shifts too. It is not only that, you can also study some kind of a dynamics. So, dynamics is very important. Okay? So, the dynamics is very important because the proteins have always have various variations in their conformation and dynamics when the substrate binds, when the substrate is converted to product and the product is released. All of these steps, the protein does not sit idle or sit stationary, there will be kind of changes. So, such changes can also be followed. So, as a small example is shown over there, where this particular ligand which is binding through these nitrogens can shift to the other nitrogen. This particular nitrogen is here. So, on the right side you have that particular. So, this is a kind of a binding changes in that. So, this kind of a species moving into this kind of a species. So, these are in dynamic equilibrium, and this dynamic equilibrium is controlled by the temperature. Okay? The lowering the temperature, the dynamic control will be more controlled, not so much of change, and if you allow it to a room temperature or a higher temperature, then this exchange will be very fast. You can also call this as an exchange between one kind of species to another kind of species. The species present on the left side to that species present on the right side. What is the difference? The difference is bound centers to the metal. that itself is bound. Now you can see there is a host of spectra here at -40, -30, -20, -10, 0, etc. So that means you are going from down to up, you are increasing the temperature from -30 to almost room temperature, a little greater than the room temperature. Okay. So therefore here you have more or less the arrested kind of a things, these exchange less and exchange is exchange arrest is less. So that means freedom is more, much more freedom, then they will be exchanging very fast. So exchanging slow to exchanging fast. So from these you can the peaks which are several here, and they become closer and they become broader and they merge, and that is what is called the coalescence behavior. So from this coalescence behavior of these proton shifts, you can measure the barrier that is present and going from the species on the left side to the species on the right side. So there is always an energy barrier that is present, and this energy barrier can be crossover by increasing the temperature. So lower the temperature, the species can be seen separately. They increase the temperature, the species interconversion is fast and you cannot resolve that too. So that means dynamics of the protein can be very well studied by NMR spectroscopy. In the previous slide we have talked about the paramagnetism, contact shifts, so therefore you can study. In here you have dynamics. So the paramagnetism not only shifts the contacts, also paramagnetic relaxation times will also. And you know the NMR spectra are governed by two types of relaxations. Okay. So NMR relaxation, okay, longitudinal and transverse. So I will not go into details of these. It's called T1, it's called T2. So these are again influenced by the protein conformation and the dynamics too. Okay. And the other thing is that they influence different centers of the, if it is a proton spectrum, different centers of the proton based on their distance. Okay. So these relaxation times, the T is proportional to 1 by r to the power of 6. So r is the distance between the paramagnetic center and the proton that you are looking at, that is being studied. Okay. So that is being studied. Okay. So therefore this phenomena can also be explored and exploited, and that is what is example is shown here. This framework is a protein framework, and there is a manganese ion, and this manganese ion is bound to protein on one side, on the other side it is bound to this particular phosphate moiety having this carbon skeleton. And you see this is the paramagnetic center, and if you see this proton is by this much distance, and this proton is by this much distance, and this proton is by this much distance, and this proton is by this much distance. So by measuring the relaxation times you can get the distance. As I told you, the relaxation times and the distances are related by the T is equal to T is proportional to 1 by r power 6. So this you can measure experimentally, and this you can obtain. Okay. So therefore in the, if you measure the relaxation times of this protein in presence of this manganese and this one, then you can get how this is oriented. Okay. From the distances you can fit into a model, and that minimize the model, and that model will give you the where it is binding, how it is binding with respect to the protein. Similarly, you can also study some protons of the protein too in terms of their relaxation times. So, therefore, the relaxation times will give you distance and that will fix the protein conformation. So, you can study the protein conformation also indirectly here by using the relaxation measurements of these that particular proton under the influence of the paramagnetic ion. So, paramagnetic ion, proton. This proton is under the observation. So, one proton is shown over there, one proton is shown over there, another proton is shown over there, another proton is shown over there. You can get their distances. Using these distances, you can uniquely build the whole structure. So, that means using the paramagnetic NMR, contact shifted NMR, paramagnetic relaxations, dynamic NMR, you can study almost all kinds of phenomena between the protein and the substrate binding. The protein, when the substrate is converted to the product, all these kinds of dynamics that is happening can be studied in that too. Now, let us slightly switch the gears to another technique. So, right now what we are seeing, nuclear magnetic resonance, where the nuclear spin is changed. Now, instead of the nucleus, suppose you take electron. So, electron is also having the spin of the positive, spin of the negative. Just like the nuclear spin plus half minus half, you also have electron having a plus half and minus half. So, therefore, we can also look at the resonance by the or transition by the electron spin, going from one type of spin to the other is not only in proton. Okay, so in case of the electron, you can see that in the absence of any magnetic field, you have the same energy, and when you apply the magnetic field, these do break up. Okay, and now the energy gap between this state and this particular state of the spin is quite large as compared to that, the quite different as compared to that of the proton, because in the proton case there is a mass involved. The electron case, the mass is not involved or mass is very small. As you know, the mass is almost 1800 to 2000 smaller in case of electron as compared to the proton. So, therefore, since the mass term comes into picture, this break will be different. So, therefore, these are found, these transitions are found not in the megahertz region, but they are found in the gigahertz region. So, therefore, in NMR, in the NMR spectra found in megahertz, this is mega, and in EPR these are found in gigahertz. Okay, so this is gigahertz. So, gigahertz, megahertz. So, therefore, that energy difference is definitely there, and this can further couple with the nuclear spin if you have, and this in this particular case 3/2 nuclear spin and further gets splitted, and both the lower electronic state, higher electronic state both get. Now, you can see the transitions going from these ones. Okay. I am not talking about all the transition rules, etc., etc. So, that will become too much more into the physical chemistry aspects, but just appreciate that these 4 transitions are possible, and these 4 transitions are shown over there here 1, 2, 3, 4. So, obviously, their gap difference is different, which means energy is different, that means they come at different values. So, instead of measuring in the frequency mode, you measure in the field strength in Gauss. So, one would basically measure in the Gauss. So, therefore, the x-axis in this is not the frequency like in the NMR, which is converted into the ppm. Here it is the Gauss. So, you keep changing slowly the magnetization or magnetic field strength, and the different transitions can be understood. Okay. The nuclear splitting under the influence of field and then the nuclear electrons, the two spins of the electrons are split in the magnetic field and then farther apart, and each of these nuclear spin the electron spin is further coupled with the nuclear spin and further split. So, therefore, you get. So, this kind of thing is this splitting is a hyperfine, and this kind of a connectivity is called super hyperfine. Okay. So, that means you can find both the nuclear spin connectivity as well as the electron spin things too. Okay. So, therefore, the number of lines will depend upon 2Ni plus 1. The I is the spin of the nuclei, N is the number of such nuclei. Okay. So, therefore, how many of such nuclei? Let us take one example to understand this. You have a vanadilyl acetyl acetone. So, V double bond O, this is called vanadyl, and acetyl acetonate. There is one acetyl acetonate, another acetyl acetonate. Each of the acetyl acetonate is 1 minus, the two of them are 2 minus, oxo is 2 minus, totally 4 minus, and vanadium is 4 plus, and therefore is a neutral. So, this is the bis acetyl acetonate 2 vanadyl actually, and the vanadium has got a nuclear spin of 7/2. And how many vanadiums are there? Only one. So, that means if you apply in this particular formula 2Ni plus 1, 2 into 1 into 7/2 plus 1. So, if you take the case of this one in the 2Ni plus 1 in the vanadyl acetyl acetonate complex, for the I for vanadium is 7/2. So, if you take 2Ni plus 1, 2Ni plus 1, so N is number of vanadiums in this it is 1, and I is nuclear spin of vanadium, and that is 7/2. So, therefore, that is equal to 2 into 1 into 7/2 plus 1, that will be 8 lines. So, you should get 8 line spectrum in this, and you can see that the 8 line spectrum is shown over there 1, 2, 3, 4, 5, 6, 7, 8 line spectrum. So, this means this is a nuclear hyperfine coupling is being seen in this example. Okay. So, now let us continue with the EPR aspects of it. Now, in the EPR aspects of it, let us look at an inorganic complex, which is a copper complex of a peptide. Okay. So, let us look at this copper complex of the peptides. So, in this we have a 9 peptide, 11 amino acid peptide, a 12 amino acid peptide. These are the EPR spectra measured. EXP refers to experimental, SIM refers to the simulated. You can experimentally measure, you can also simulate using the parameters. Then all that you see that the 11 and 12 and whereas 9. So, there is some little hyperfine kind of a couplings that you see different, but otherwise very similar kind of things. Okay. And this can be understood from, see, this is the sequence. What is binding in this is the 9 a cysteine, a histidine, and a methionine. In case of 11, a cysteine, a histidine, another cysteine and a histidine, and in the 12, a cysteine, a histidine, and a methionine. Okay. So, you have all of these are bound to the copper center. Of course, copper in all these things is copper 2 plus. No point in looking at copper 1 plus. You know why? Why copper 1 plus cannot be studied? Copper 1 plus is a D10 system, copper 2 plus is a D9 system. So, D9 system will have an unpaired electron, D10 system will not have an unpaired electron, therefore, copper 1 cannot be studied at all. Okay. So, that is the kind of thing. In fact, in some enzymes where copper 2 plus is there, you look at the EPR spectrum, which is coming from the copper 2 plus, very nice. Then you add some reducing agent and the copper 2 plus becomes copper 1 plus, and then it turns into from D9 system to D10 system and becomes EPR inactive. So, EPR active to EPR inactive too. In this case, all of these are EPR active and that is because copper 2. Now, this is being analyzed better in this particular, in the next slide, and this is the slide. So, there are 3 copper complexes as you can see, and from the EPR spectra you can get the shift that is found, which is found in the form of the Gauss as a position. Okay, you can get that kind of thing. Is also referred as a G value in many cases. So, the G value is plotted in terms of the Gauss and the coupling ones. Let us just for a while let us look at these ones, and the distance between these ones is the coupling values. So, as you can see from here to here, here to here, here to here, similarly here. So, these are the coupling values, which is referred as the A values. So, the A is a hyperfine coupling, and this is the position of the peak, the G. So, the Ga to G correlation you see so nicely connected by a straight line. So, this is all not important, you do not go through all these things, all that you need to look at is this particular thing. So, therefore, the positioning, the EPR peak position versus the connectivity between these thing in terms of the hyperfine coupling values are correlatable from one to the other, and that is what we can make in this. And as I told you that you can also study not only copper, many other paramagnetic things like manganese can be studied, and iron can be studied, some molybdenum can be studied, some of them in their oxidation states where they show the paramagnetism. For all of them one can study. And of course, the interpretation of the EPR is somewhat difficult compared to the other spectroscopy that I have talked to you earlier. Okay. So, let us look at another technique. Another technique is the electrochemistry. So, the electrochemistry, this we are talking about the cyclic voltammetry. So, electrochemistry is basically you add an electron to the system or molecule, you remove an electron to the system or a molecule, what happens to it? How do one measure in terms of what happens? So, this is what is basically studied. So, one of the ways is that you apply a potential or vary the potential and measure the current. So, if you take apply a potential, vary the potential and measure the current, therefore, the current versus the voltage is called the voltammetry. Current versus the voltage is called the voltammetry. Voltage versus the current is the voltammetry. Voltage versus current. So, you apply voltage versus current is voltammetry. Of course, so what you do in this, you keep applying the potential and measure the current. So, in this case, why it became cyclic? Just follow me as I take this cursor. Let us say I took a solution containing a compound which is electroactive. I start from this particular voltage and I keep increasing the voltage towards this direction. So, it goes along with this, okay, and there is a sudden increase in the current of this, and at this stage I reverse the potential. So, if I reverse the potential, it does not go through the same, it comes from the another. So, it comes through this, so it comes through the whole thing and then goes back. So, I start from V1, go to V2 and reverse switch the direction of the potential and then come back. Potential has a sign, a positive potential, negative potential. So, going from this to this, increasing means going towards the positive direction, and going from here to here is you are going from this potential and decreasing, it is a negative side. So, you have a positive side, you have a negative side. Okay. So, you can reduce, you can reoxidize kind of a species, and that is all. So, it becomes a cyclic. So, therefore, it is a cyclic voltammetry, going from left to the right and then reversing the potential and coming back, and this is where you can make the whole difference in this particular methodology you can make. For example, you take a electrode, here it is shown example, a silver electrode, and take a solution of the protein, a metalloprotein, and a metalloprotein containing the iron center, iron metalloprotein, iron with the 2 plus and going to iron 3 plus. So, that is what oxidation, and this one the Br going to Br minus is what reduction. So, this oxidation of this is connected with this reduction, and this reduction is connected with the electrode. So, from electrode you go from this Br minus to Br. Br minus to Br is oxidation, and this oxidation will give away the electron, and this electron will be picked by the Br, and this way, or it will be picked up by this to return back, and in the process it will activate the metalloprotein iron 2 plus to iron 3 plus. So, therefore, it is coupled with this. So, everything is coupled to the electrode. Okay. So, at the electrode you are releasing the electron, and this electron is being taken up by this, and as a result of this process is coupled with this and going from iron 2 plus to iron 3 plus, oxidation. So, similarly you can do reduction as well. So, you can do oxidation of the protein, you can do reduction of the protein, everything is possible by changing the potential here. So, and you know that in case of the metalloproteins and metalloenzymes, bone in disguise, you have metal ions having different oxidation states, therefore, you can take the protein from one to the other. And the protein also has a conformation, therefore, the potential is also affected by the conformation of the protein as well. So, the medium, the protein conformation, and the redox going between the positive to the negative, all of these kind of things. Okay, let us take one example here. So, this is an electrode, the electrode is modified and modified by this kind of thing, and this particular thing is connected with the protein. So, this whole background kind of a thing, spiral etc. is a protein. In that protein there are centers, one, there is another 2, 3, 4 etc. and these are all electron transfer centers, and primarily these are all iron sulfur centers. And then here you have actual reaction center where the reaction occurs from H2 going to 2H plus, H2 to going to 2H plus 2 electrons is what? Oxidation. So, H2 going to 2H plus electron to H2 going to 2H plus 2 electrons. Okay. So, this is an oxidation process. This oxidation process can be identified, it can be studied, and the electron is transferred from where? From the electrode through these to these, from there to here, from there to here, from there to here. At the end, the reaction site is this one. So, it is at this side the hydrogen goes to proton, and but to get there you need this process. So, this entire process is controlled by the iron sulfur proteins having different redox potentials. So, having different redox potentials is a boon in disguise. That is why nature has identified its own or managed its proteins to have centers of iron sulfur with different potentials. I will explain this more details when I come to the iron sulfur proteins story in this. A simple example is shown over there. A simple example is that an electrode modified with this moiety, which is connected to this particular amide. So, this amide having the phosphorus centers bound to the nickel center and another ligand. So, this whole thing you can do a redox, and this particular molecule can convert H plus to H2 and then H2 to H plus. So, they can do both reversibly in this. So, H2 getting in H plus 2. So, redox kind of thing. So, therefore, one can basically look at all these things, look at different kinds of redox systems here you have. As you go from top to the bottom, you are having the reduction potentials are becoming less negative or rather more positive. That means more reduction is favorable. How do you understand this? You can understand this by delta G is minus NFE or E naught. So, if the potential is minus, this minus into minus is plus. If the potential is plus, plus into minus is minus. So, more reduction potential positive means this will be minus, more feasible. So, N is number of electrons involved in the reaction, and this is Faraday constant. So, the more positive potential will make delta G more negative. That means reduction potential more positive means reduction is more favored. So, as you go from this to this, more and more reduction is favored. If you go in the reverse direction, more and more oxidation is favored in this. Let us see this in the context of an example of a copper proteins. You can see here these are all small molecules up to here, and if you go down here, this is a lacase. This is an enzyme, copper, ceruloplasmin is an enzyme, azurin is an enzyme, plastocyanin is an enzyme. So, why are we studying all this? We are studying all this to find out what kind of centers are present in the proteins. So, therefore, we are taking a small molecular copper complexes here. This copper complex between 2 plus 1 plus, potential is plus 0.59. The next complex with the chloro is plus 0.40. Similarly, you go to imidazole kind of thing, plus 0.26. You go to the pyridine, plus 0.197. So, your potential is smoothly changing from plus 0.6 to over this. And if you look at so what is happening? As you go down further and further, the nitrogen kind of a bindings are reducing, oxygen bindings are increasing. You go to the copper alanine, you have mainly the lot of carboxylate oxygens are being bound. Therefore, the potential is basically converted from positive to the negative. So, therefore, redox potentials are dependent on what is directly bound to the metal center. They are also important or they are also dependent on the protein conformation as well. All those parameters will affect. Okay. So, going from nitrogens to the oxygens to the minus containing oxygen, carboxylates, etc., the potential is. Now, you look at the peptides, the proteins, the lacase plus 0.4, ceruloplasmin plus 0.39. So, these are all roughly very similar. What it means? Basically, in these proteins, you have a lot of nitrogen or imidazole binding is involved in all of these. Therefore, their redox potentials are very similar to those of these particular derivatives. Okay. So, so what we have seen, we have continued with the NMR in this lecture, then we have continued with the EPR, which is an extension. Then we have looked at the electrochemistry, and we started with the redox potentials in the terms of the cyclic voltammetry. Then we tried to compare these redox potentials going from positive to the negative as a function of change in the binding centers are changing, because as you go from nitrogen centers to the oxygen centers to the negatively charged oxygen centers, the redox potential changes from positive to less positive to negative. Okay. So, what does that mean? What that means is that the reduction is less favored, the oxidation is more favored. When you have more positive potential, more reduction is favored in that. Now, if you compare these things with the enzymes, so the enzyme, the lacase and the ceruloplasmin, the azurin and the plastocyanin, they are all plus 0.4 around that. Okay. So, that kind of a potential is certainly coming within this range of this. So, therefore, one can explain that in these proteins, the protein centers are having a lot of imidazole binding, nitrogen ligand binding, maybe even some sulfur ligands binding as well in all these aspects. Now, you can see that so we can use a variety of spectroscopy techniques. I have talked to you about the NMR, then we have talked to you EPR, then I have talked to you redox potentials. A few more techniques I will talk in the next class. Then with that we will finish the techniques part of it. Thank you very much.